All right, so we are to the last 4 weeks of the semester, right? 8 class periods for a Tuesday, Thursday class. Then we've got finals week again. Our final exam is going to be take home, no in-class portion, but we will meet to hand the take home in and go over it to some degree, and maybe also just have some fun, have some food or something like that during our final exam time. And our topic is going to be regression. Chapters 11 and 12, I believe, in the book. Simple linear regression, which is with one explanatory variable, and multiple linear regression. Being in prob and stats, in the past, you have learned a little bit about regression, but it's always worthwhile to review. I've taught regression many times, but I always feel like it's a good idea to review it every time that I teach it, because like I've said to you before, I do certainly forget things like most people. It's not something I've got stored away completely in my memory. I have to review consistently. Today, I want to approach it from what you might say the most simplistic approach, just thinking of lines of best fit, okay? Not really thinking about the meaning of the word regression. We do want to spend some time talking about the meaning of the word regression. Why do we call it linear regression? Here I want to think of it as a line of best fit, or you could also add least squares line as our technical, a bit more technical description of what it means to be a line of best fit. So we want to approach this by hand as much as we can here at the beginning of class today. And then we want to transition into the technology. And there's going to be 4 bits of technology that we're going to be working with. We want to get comfortable with all the technology and also compare, what's more convenient, that kind of thing. So 1 bit of technology is just a TI graphing calculator. Hopefully non-TI graphing calculators are also similar. Another bit of technology is a spreadsheet. Another bit of technology is Mathematica, and another bit of technology is R. So we're going to start to learn a bit of R. Now, I'm plenty familiar with calculators, spreadsheets, and Mathematica, but I'm a newbie with R, as probably many of you are. So we'll be learning it together. I shared with you a video yesterday that is, I think, a pretty good introduction to the basics and has some nice data sets that we can look at. But we want to also, just today, learn even how to enter some data like the data that you see here and do some basic things with it. So we got 4 data points here. Write those down if you haven't done so. These particular data points do result in a line of best fit, a least squares line, that the numbers turn out to be fairly nice. So that's what I want to pick these data points for. More realistically, we do want to deal with real life data sets that have applications that can be interpreted in terms of real life. But today we want to just think about the mechanics of it. So what is the goal? The goal here is to find, yes, a line of best fit. More officially, more technically, a least squares line. Find a linear function, really. Linear function f of x. Typically, we write that as mx plus b, and I could certainly do so. However, in statistics, to allow ourselves to go beyond simple linear regression, we use this kind of notation. We use b sub 0 for the intercept and b sub 1 for the slope. So b sub 0 is the intercept, and b sub 1 is the slope. We want to find a linear function like that, that best fits, in quotes again, the data. But what does it mean to best fit the data? Here's the official way to say it. We want to minimize the sum of the squares of the errors in using the line to estimate the data. Error here is synonymous with another word called residual. You could also say we're minimizing the sum of the squares of the residuals. Error is synonymous with residual. the ith error, which I will more commonly call the ith residual, though it is denoted by E sub I, E for error. This is not the number E. You could think of as a word equation being observed sub I minus predicted sub I. I here for this data set with 4 data points is 1 or 2 or 3 or 4. Shorthand, the observed is called Y sub I, and the predicted is called Y sub I hat. Putting a hat, as we've done with proportions, is emphasizing that we're trying to estimate. Think of that as an estimator in the abstract if you wanted to. But how do you find Y sub I hat? You use the unknown linear function. So this can also be written as Y sub I minus f of x sub I. F of x sub I, if I plug in these x values from the data set into this function, are not necessarily going to equal the y's. In fact, they would only equal them if these were all on a straight line. But I purposely picked these things to not all be in the same straight line. So we're going to get a function here, a linear function that's not going to go through the data points exactly, just approximately. We want to try to approximate the trend. In fact, this is sometimes called the trend line as well. Let me add that. Trend line. In fact, if you're talking to people who use linear regression a fair amount for making predictions about the future, oftentimes, they will perhaps most often call it a trend line. We're after the trend line. We've got to plug this into the function. We can now write this as yi minus in parentheses. There's the function b0 plus b1 xi. And then finally, we can distribute the minus sign through the parentheses. So we can write this as yi minus b0 minus b1 times xi. So there's a lot of different expressions for the same thing. You could think of it as error or residual. You use the notation E sub I. Again, E is not the number E. It's not 2.71828, blah, blah, blah. It's the ith error, the ith residual. I remember it as observed minus predicted, and that's nice because that goes in alphabetical order. O comes before P. Yi, the y's from the data set, are the observed values. Yi hats are the predicted values that come from the unknown linear function that we want to find. We can use the formula for that function to rewrite this ith residual in this way. But remember, I said a few minutes ago, the goal is to minimize the sum of the squares of these things, and that's why it's called a least squares line. Minimize the sum of the squares. These names, line of best fit, trend line, and least squares line, are all pretty intuitive. What's less clear is why we call it linear regression. Why do we use the word regression? That has to come later. I have to explain that perhaps on Thursday here. The sum of the squares of the residuals, also called the sum of the squares of the errors, is denoted by SSE, sum of squares of errors. Sum of squares of errors. But of course, since error is synonymous with residual, it's also sum of squares of residuals. So that is going to be a summation. In general, I goes from 1 to n, though for our problem, n is 4. of the EIs squared. Which then, because the EIs end up equaling this thing right here, because it comes a sum I goes from 1 to n of these things squared. Yi minus B0 minus B1 xi quantity squared. Let's go ahead and do this right away in the general case. Yeah, let's do it. Let's do it. I changed my mind there on the spot. Let's do the special case first with our data set, and let's do the general case after that. This is an applied stats course, and we are going to do applications, but we're going to continue to try to do theory too, because theory helps you understand the ideas and helps you apply it more broadly. So we want to plug in these numbers for the x's and the y's. Already without a summation sign here for our data set, where n is 4, and our data set. This becomes SSE. I'm also going to add function notation in here. SSE, since B0 and B1 are unknown, is really a function of B0 and B1. I'm using function notation there. The first data point was x1 was 1 and y1 was 2. So this becomes 2 minus B0 minus x1 was 1. So I get a minus B1 squared. That's the first term in the sum, because the first data point was x1 is 1, y1 is 2. Second data point, coming back up here, is x2 is 2 and y2 is 4. Plug in y equals 4 and x equals 2. Third data point, x3 was 3 and y3 was 5. Plug in the fourth data point, 4, 7. Y4 is 7 and x4 was 4. This is the quantity we want to minimize. Least squares line. It's a function of two variables, multivariable calculus. Okay, now I know a few of you maybe haven't had multivariable calculus. Probably most of you have, but maybe a few of you haven't. Probably all you guys have, I guess. Differentiate with respect to B0 and B1, partial derivatives. I won't bother with the function notation there. What's the derivative of SSE with respect to B0? You could expand this all out, square all these things. But to tell you the truth, it's simpler not to. Don't bother. Just differentiate these as they are. You got to use the chain rule. So in each case, you're going to bring down the 2. And with the derivative with respect to B0, the coefficient of each B0 inside the parentheses is -1. So the chain rule is just going to give an extra factor of -1. Make sure you are checking my work to make sure I don't make a mistake. And tell me if you see any mistakes. Let's go ahead and simplify this. See if we can simplify it in one step here. First of all, the constant terms, you're going to get 2 times 2 times -1 is -4. With these and that, you're going to get -8. So -4 plus -8 is -12. Right? Do the calculations in your head with me. -10 is going to give us down to -22, and then another -14 is -36. Double check it for me. That's right. I'm going to double check it too. I think that's right. Okay, what about the coefficients of B0 and B1? They're going to become positive because negatives, two negatives being multiplied will give us positive. So for example, here you're going to get negative 2 B0 times another negative 1 is positive 2. So you're going to get a positive 2 contribution to the coefficient of B0. Here you're going to get another positive 2. In fact, they're all going to be positive 2. There's 4 of them. They're going to get positive 8 B0. And then for the B1 coefficient, it's going to be positive as well, but not 8. It's going to be 2 plus 4 is up to 6, plus 6 more is up to 12, plus 8 more is up to 20. Look right to people? Okay, I see people nodding. That's good. Now let's differentiate with respect to B1. Going to be a little bit more chances of making a mistake because the chain rule coefficient's not going to always be -1. But it's going to be a pretty similar calculation. With the first one, it'll get a factor of -1. With the second one here, you're going to get an extra factor of -2, right? Because -2 is the coefficient of B1. With the third term, you get an extra factor of -3. And with the fourth one, you get an extra factor of -4. Okay, so the constant terms, they're all going to be different, excuse me. The constant term you'll get here, you'll get -2. And then careful here, a -16 with this one, 2 times 4 times -2. -2 plus -16 is -20. Thank you, -4. And -16 is -20. I just was saying -2. So -4 plus -16 is up to -20. Here we have a 10 and a 3, that's 30. So we're down to -50. And then 14 and times 4 will be 56, -106. Yes? Coefficient of B0. Here you're going to get a 2. Here you get a 4. So we're up to 2 plus 4 is 6. Here we're up to 6 more is up to 12. And finally, 8 more is up to 20. Look good? 20 B0. It's a way to help you stay awake. Okay, do the calculation in your head with me here. Coefficient of B1. This one gives you a 2. This one gives you an 8. 2 times 2 times 2. They're all 2 negatives making a positive there. So we're up to 10. 9 times 2 is 18, bringing us up to 28. And then 16 and 32 times 2 is 32. So we're up to 28 plus 32 is 60. 60 B1. Look good? All right, so set these equal to each other. Or set these equal to 0, excuse me. And solve for B0 and B1. Oh, should we have some fun with a matrix? Let's do some row operations with matrices. Not just for fun, but also partially because in chapter 12, we are going to deal with matrices a lot, actually. So let's go ahead and do that. I could divide everything by 4. In that one, at least. 2 in this one. And I can also put the constants on the other side. And I should if I want to use an augmented matrix. So I'm going to divide everything by 4 in that one. So I'll really get 2B0 plus 5B1 will equal, that divided by 4 will be 9. So in my augmented matrix, I'll get a 2, then a 5, then a 9 to the right of the dashed line. I like making dashed lines in my augmented matrices. Does Auk do that when he teaches linear? And you're doing row reduction and augmented matrices? Yes, no, do you not remember? Okay, he does. It's just to remind you that whatever's to the right of the dashed line is the right-hand side, the numbers, not the coefficients of the unknowns. And with the second one, I can divide everything by 2 and get a 10 and a 30 and a 53. Okay, divide the top row by 2. To get the second row, I'm trying to get a 0 there, so I can think about the first matrix here. Multiply this first row by -5 and add it to the second. 2 times -5 is -10, plus 10 is 0. 5 times -5 is -25, plus 30 is 5. 9 times -5 is 45, plus 53 is 8. Look good? Double check those two. Yeah, I think that's right. Now divide the second row by 5. And now multiply the second row by -5/2. Add it to the first row to get a 0 there. 8/5 times -5/2. The 5s will cancel. We'll get -4. Right? 8/5 times -5/2. Be -4. -4 plus 4.5 will be 1/2. Yeah, the numbers come up fairly nice. Even have exact decimal representations that are not repeating. Looks like B0 was the first unknown. That's 1/2, 0.5. And B1 is 8/5 or 1.6. Let's go ahead and make a hand graph to see how good the fit is just by hand. So plot these points. Try to do a halfway decent job. One, 2, 3, 4 are the x coordinates. And the y coordinates go from 2 up to 7. One, 2 is the first point. 2, 4 was the second point. I should probably be over here to try to make this a better drawing. Third point was 3, 5. Fourth point is 4, 7. And what we found is the line of best fit has an intercept of 1/2 and a slope of 1.6. So as x goes up by 1, y goes up by 1.6 from 1/2 to 2.1. Oh boy, this drawing's not so good. Maybe something about like this. I'm sort of, yeah, I'm not doing a great job. Yeah, I mean, with a quick drawing, quick rough sketch, that seems like a pretty decent fit. I'm not sure how accurate my drawing is. Let's go ahead and compute each residual and see which ones are positive and which ones are negative. So E1 is going to be Y1 minus Y1 hat. Y1 was 2. What's Y1 hat? You got to plug X1 into the regression equation, which is going to be f of x equals 0.5 plus 1.6x. Plug in x equals 1 into that. 0.5 plus 1.6 times 1 is going to be 2.1. 2 minus 2.1, negative 0.1 is the residual, the first residual. Corresponding to the fact that I drew it correctly, the second coordinate of this point is below the second coordinate on the regression line. This point has coordinates 1, 2. This point has coordinates 1, 2.1. When the residual is negative, that's corresponding to the point being below the regression line. Makes sense to think of that as a negative residual. Looks like, if my drawing is accurate, the second point has a positive residual. It looks like the second point is above the regression line. Let's see if that's the case. E2 is y2 minus y2 hat. It's going to be 4 minus 0.5 plus 1.6 times 2. That'll be 4 plus, or 4 minus, excuse me, 3.7. Yes, positive 0.3. That point is above the regression line. E2 represents that positive distance there. E1, since it's negative, doesn't technically represent a distance, unless you think of distances as having a sign, positive or negative, depending on whether they're above the regression line or below the regression line. And that's probably an okay way to think of it. So E1 is a negative residual. The sign distance is negative 0.1. It has a negative sign emphasizing it's below the regression line, but the vertical distance itself as a positive quantity is the absolute value, that positive 0.1. Looks like perhaps E3 is negative. Let's confirm it. So the third coordinate of the third point is 5, and if I plug 3 into the regression line equation, 1.6 times 3 is 4.8. Plus 0.5, yes, I'm going to get a negative residual, negative 0.3. Do you have a guess as to what the fourth residual is going to be without actually calculating it? It's going to be positive 0.1 because the residuals actually have to add up to 0. These two already add up to 0. This one's negative 0.1. This one's got to be positive 0.1. And it is corresponding to the fact that the point's going to be above the regression line, unlike how I drew it. The regression line actually goes below this point. So it's 7 minus 0.5 plus 1.6 times 4. 7 minus, that'll be 6.4 plus 0.5 is 6.9. Positive 0.1. Let's also go ahead and compute SSE. All that means SSE is the sum of those numbers squared. So negative 0.1 squared plus 0.3 squared plus negative 0.3 squared plus 0.1 squared. So that'll be 0.01 plus 0.09 plus 0.09 plus 0.01 will be what? 0.2? Looks like that's the value of SSE for this example. Evaluated at the intercept and slope of the actual least squares regression line. No other values of B0 and B1 will give you a lower value of SSE. Any other line that you use, any other slope or intercept or both, will give you an SSE value that is bigger than this. This is minimized. Is it a good idea to minimize this? Is that the best choice to make? I mean, why not just minimize the sum of the absolute values of these residuals? Wouldn't that be simpler? Well, you could try that. However, this has the benefit of being easier to differentiate, for one thing, than absolute values symbols. That's one benefit of this. Another benefit is the general formulas are going to come out fairly nice. Now, I do want to use technology to confirm all this, but let's do one more derivation. Let's derive this in the general formula, okay? So I think it was worth deriving B0 and B1 for this particular example, but let's also differentiate this in general and come up with the general formulas. We do want to understand and be able to remember even general formulas, even though the final exams take them. And by the way, the final exam will be completely on regression, okay? Not that I want you to completely forget the past, but I think it's probably best to focus on regression, chapters 11 and 12. Let's do it in general. Doesn't sound like much fun, but I hope you see that it actually, if you grit your teeth and grin and bear it, you might say, yeah, it's kind of fun, actually. SSE B0, B1. Again, the formula ends up being summation I goes from 1 to n of yi minus B0 minus B1 xi quantity squared. We're going to derive this with calculus here in the simple linear regression case, partial derivatives again. Though in chapter 12, when we approach this with multiple regression, we're going to think more in terms of linear algebra. You can actually think of it either way. We're going to use matrices and vectors. And I don't know if you, in linear algebra, if you did a little bit with least squares or not. You remember? Anybody remember? Yes, no? Not sure. You can find it in your linear algebra book. I think it's in chapter 6 on orthogonality. You can approach least squares using linear algebra without calculus, actually. I mean, you might say calculus is still in the background, but you can solve for B0 and B1 and multiple linear regression where you have more B's, like a B2 and a B3 and a B4, et cetera, using linear algebra. But let's do it with calculus. Partial derivative with respect to B0. You're used to this kind of thing, right? With differentiating for maximum likelihood estimators, having to deal with summation signs still. Just, we're taking the derivative of a sum. That's the sum of the derivatives. When we differentiate each of these, we use the chain rule again and get an extra factor of -1 when we differentiate with respect to B0. And then you can distribute the -1 through. You can also separate the sum of these things into a bunch of separate sums and factor out any constants. So you could factor out the 2. You could get a 2 times the summation I goes from 1 to n of -yi, and I can also bring a negative sign out in front and do that. And then with the next one, I'd have a 2 out in front. And the B0 is actually a constant with respect to the summation. I'm really going to get 2n B0 with that one, because the B0 is a constant with respect to the summation, doesn't depend on I. Adding up n B0s is going to give me n times B0, and then the 2 stays there. Ultimately, the 2, when I set this equal to 0 to solve for B0 and B1, the 2 is going to cancel. So I'll leave it there for the moment. With the last term involving the xi, the B1 is a constant. It can be factored out. 2b1, but I still have a summation of the xi's. Okay, I will be setting this equal to 0, ultimately to solve for the B0 and the B1. And the 2 again will cancel. Partial derivative with respect to B1. It's going to be something somewhat similar, except with the chain rule. When you differentiate with respect to B1, you get an extra factor, not of -1, but of -xi. Distribute that through, separate the summations. Let me write it down here. First one, you're going to get a 2 out in front with a negative sign, and a summation of the products of xi times yi. I'm distributing the xi through the parentheses when I do that. With the next one involving the B0, the 2 in the B0 once again can come out in front, but now it's not times n, it's times a summation of the xi's. Maybe if you could ask them to not be so loud. Is there, can you see them? Are they in the other room or what? Huh. They're sitting on the floor. This is very loud. Is that louder than usual? Yeah, okay. Thanks, Anna.
Yeah.
And then the last one's going to be involve the B1. Factor out of 2B1, have a summation. I goes from 1 to n of xi squared. So we'll set that equal to 0 as well. And remember what the goal is. The goal is to solve for B0 and B1. The x's and the y's are constants in this. Cancel all the 2's. You can divide both equations by 2's. So what you're going to get is you're going to get a system of linear equations. Things that don't involve B0 and B1, I'm going to put on the other side. They also involve the negative sign. So when I put them on the other side, I'll get a positive sign. I'll have a 2, I got rid of the 2, sorry. NB0 plus B1 times the sum of the xi's equals the sum of the yi's. That comes from this first equation, dividing everything by 2, canceling all the 2's, adding the sum of the yi's to both sides, gives you this. With the second equation, cancel all the 2's, add the sum of the xi times yi's to both sides. And what you're left with is B0 times the sum of the xi's plus B1 times the sum of the xi's squared equals the sum of the products xi times yi. There's your system of equations. This has a name. It's called the normal equations. And it's certainly a system that you could just write down given any data set, figure out the sum of the x's, sum of the y's, the sum of the xi squareds, the sum of the xi's times yi's, and also the value of n, and write down your system. What would it be for our example? Actually, that's worth doing. For our example, with our data, and going back to these data here, the sum of the x's, I goes from 1 to 4. It's 1 plus 2 plus 3 plus 4. 10. Sum of the y's, 2 plus 4 plus 5 plus 7. It's going to be what? 18? Yep. 18. N is 4. Sum of the xi squareds. Got to square those x's. 1 squared, 2 squared, 3 squared, 4 squared. It'll be 1 plus 4 plus 9 plus 16. 1 plus 4 is 5, plus 9 is 14, plus 16 is 30. And the sum of the products of each xi times each yi will give you 2 plus 8 is 10, plus 15 is 25, plus 28 is 53. Oh yeah, these numbers are looking familiar. So we get, combining these things, the system 4B0 plus 10B1 equals 18, and 10B1 plus 30B, or B0, excuse me, 30B1 equals 53. Yeah, if we divide the first equation, everything by 2, that gives us the same thing as we got in this matrix. Okay. So it's going to be the same solution. B0 is 0.5 and B1 is 1.6. Well, let's try, again, before we use technology, to solve this by hand. Really? All right, yeah. Let's solve first this equation. I could try to do row operations. Let me do it with substitution. Let's solve this first equation for B0 in terms of B1. Subtract this from both sides and divide everything by n. This is worth doing. Subtract that from both sides. And divide everything by n. And you'll get that. And this is worth noting that this also equals this. Break it into 2 fractions, and that obviously is y bar minus b1 times x bar. Hey, that's worth remembering. Looks worth remembering, right? The intercept is always the mean of the y values minus the slope times the mean of the x values. And that has a deep meaning. Meaning. It means that the point whose coordinates are x bar and y bar is always on the regression line. Now, that's not likely to be a data point, right? It's not likely that you're going to have a data point whose coordinates are the mean of the x's and the mean of the y's. But that point, which is probably not a data point, will be on the regression line. What is it in our case? The mean of the x's would be 10 divided by 4 is 2.5. The mean of the y's would be 18 divided by 4, which would be 4.5. 2.5 comma 4.5 is a point on the regression line. Should make it green. 2.5 comma 4.5, right around there. It's not a data point, but it is a point on the regression line. How is that helpful? Well, it can help you draw the regression line by hand if you had to. That's one thing, way it's helpful. At least to eyeball it, if nothing else. Okay, you might say it's a minor bit of help since we have technology, but it's worth noting. What about B1? What do you do when you do the substitution method for solving? If you solve this equation for B0 in terms of B1, you'd want to then substitute that into the second equation in place of the B0. In place of B0, I could put any of these 3. Let me put this form, even though it's more complicated than that. I'm going to want to not have means in my final formula for B1. Well, no, maybe I'll put the second form in place of B0. I'm putting the I goes from 1 to n every time I write these summations. Sometimes people are a little sloppy and don't bother. It's just understood that I goes from 1 to n. And that's typically going to be fine if you do that, but I'm trying to be a little extra careful at the moment. So I took this second equation and replaced B0 with this thing. And there's what you get. Goal here would be to solve for B1. I'd want to combine these two things probably with a common denominator, perhaps. Or perhaps not. Okay, let's actually not do that. Let's combine these two terms though and factor out a B1. So I'll have B1 times the summation of the xi squareds minus the summation of the xi's divided by n. And then on the other side of the equation is going to be everything else that'll come from the product of this with this and the term that's already over on the right side. I got to subtract the product of these two things. Now just divide everything by this. So you can write B1 as, this is not the final form you see in the book, but I like this form, even though we got fractions within fractions. The thing on the right here, the summation of the products of the xi's times the yi's minus this fraction there. Sum of the xi's times the sum of the yi's. You got to add those things up before you multiply the summations. All divided by this thing in parentheses there. I think I made a mistake here somewhere. Something's wrong. Oh, I know what I did wrong. I forgot to distribute this through up here. This should be squared here because I got to multiply these two summations. Which makes this thing be squared as well. I forgot to multiply those. I like this form of the answer because it's related to something else that I remember and I think is worth remembering. Turns out you can prove, I'm not going to show you the details, that the numerator equals this summation and the denominator equals this summation. Maybe I'll make that a homework problem, is to verify that. Oh, I made a mistake. Sorry. Sorry. You can prove the numerator, it's a different summation. It's this summation. And the denominator is the original thing and I had that had in the numerator there. The denominator is this summation. Okay, I think I'll make that a homework problem is to verify that. You can just verify it for both the numerator and denominator. It's just a matter, I would probably start with these summations and use the FOIL method here and simplify, and then you'd have to square this with FOIL as well and simplify. It's not too hard, maybe a little tricky, but not terribly hard. And the reason that's good is because I give names to these things that are somewhat standard names. I call the bottom here SS, sum of squares, sub XX, because the x's are being squared, so to speak. Actually, the textbook uses slightly different notation, but this is the notation that I like. And it's somewhat standard. SS stands for sum of squares. I'm summing some squares. And those squares involve the x's. Why did I put two X's? Well, this is not a sum of squares in the numerator, but I go ahead and call it SS anyway, even though it's not a sum of squares. But the subscripts are an X and a Y because there are an X's and Y's in the summation. This is literally a sum of squares. This is not literally a sum of squares, but use the notation anyway. And that's something fairly easy to remember, which is why it's one way I remember this thing. This is not the final form of the formula in the book. In the book, they multiply the top and the bottom of this by n to get rid of the fractions within fractions. And they write B1 as n times the summation of the products of the x's and the y's minus this thing without the n, product of the summation of the x's with the summation of the y's. And at the bottom, something similar happens. And they write it like this. All right, we've got 15 minutes left. Let's use technology. Start with the calculator. You want to be comfortable with all these methods. We are going to see, well, you want to just be knowledgeable about different ways of doing this kind of thing with technology, for one thing. And for another thing, we want to compare, what seems like the best tool in a given situation. And sometimes it's just dependent on what technology you happen to have. So with the TI graphing calculator, start off by going to the stat menu, stat button. Hopefully yours is not too different than this. And the first thing you want to do is the edit menu. Got a bunch of different columns for different lists. L1 can correspond to the X values, L2 can correspond to the Y values. The natural thing to do, go back to our data set here. Plug in the X values, 1, 2, 3, 4. L2 is going to be the corresponding Y values, 2, 4, 5, 7. Let's go ahead and make a plot first. You can make a scatter plot, effectively what I made by hand here, of just the data. You can also put the regression line in there, but I'm not going to do that right away. Notice on a TI-84, at least, that my stat plot menu seems to be above my y equals, but I got to use my second function. Second function, stat plot, gives me a menu that looks like this, and all these plots are turned off, so I have to turn them on. Plot 1 by default has L1 and L2, you can see as the lists that are used. If I enter this and switch it to on, make sure the lists are correct, L1 and L2. And the type is going to be the first option there. That's going to be a scatter plot. That's good. Quit out of that. I'm forgetting, I haven't done this in a while. Do I just hit graph? No, okay. Stat plot, it's on. I should pick a good window for one thing. Now I'm in the window menu. Maybe like that. Okay, now I just hit graph and there they are. There's the 4 points. If you go back to the ordinary y equals screen, if you already happen to know the regression line, you can plug it in. It was 0.5 plus 1.6x. Of course, by the commutative property for addition, you can also write that as 1.6x plus 0.5. You all know that. Hit graph again, you'll see the regression line. Okay. Looks like maybe it's going through that point, but we know it's not. The residual was non-zero. It's going to be a very rare thing for a regression line to ever go through any data point, even if you got hundreds of data points. It would be very, very unlikely for your regression line to go through any data points exactly, but it theoretically can happen. What about if you didn't know what the regression line was? If you go back to the stat menu and calculate, you can compute it, lin-reg. My calculator is set up to compute something else when I do this. There's A, that's the slope, B is the intercept. You got to look at the equation to know which one is which. Notation is not consistent with B0 and B1. What are these two other things? Maybe your calculator shows them, maybe it doesn't. If it doesn't, can you make them show up? Well, what are they, first of all? R is called the correlation. As a descriptive statistic, we talked about correlation in prob and stats more than this class in chapter 5 as a theoretical idea related to covariance. This is related to the theoretical correlation for random variables. It's not the exact same thing. This is a correlation of data. R squared is the squared correlation. Does that have a name? It actually does. It's called the coefficient of determination. We'll see that R squared, excuse me, R squared in a sense is a better measure of the strength of a linear relationship. And that's why it's shown. But if your calculator doesn't show make it show up, you should be able to fix that by going to the catalog button. It's above 0 on mine. And going down to the D's, I can go alpha D, I think, to go down to the D's, or the alpha already pressed there. Okay. To the D's, and look for diagnostic on, and enter that, and it'll say done, hopefully. And then when you go back to lin-reg, it should show the correlation and R and R squared as well. Why you have to do that, I don't know. It's like, why not just make that the default? I don't get it. But hopefully that works. Let's move on to a spreadsheet. That's not what I wanted. Where'd my other window go? Oh, I have it open. Let's just do the quickest way of getting the regression line. Oops, without formulas. Of course, you can program the spreadsheet to do the formulas that we've used. I won't bother with that today, though maybe we'll look at it on Thursday with bigger data sets, and we'll also get some intuition about things. But if you're just after the answer as quick as you can, at least in Google Sheets, I think I like Google Sheets for making graphs better than I like Excel, generally speaking, especially for histograms. You can highlight the data. I included the X and the Y in there. And go to Insert Chart. It did pick a scatter chart by default, which is good. And we can customize it. Oh, I always have to remind myself how to do this here. Okay, there we go. Under customization, under series, you may want to write this down. In Google Sheets, at least, if you go down under series, you can add the trend line, which does mean the regression line. You can show R squared, the 0.98, and use equation for the label. And there we have it. y equals 1.6x plus 0.5. The r squared looks like it's part of the equation, but it's not. Okay. With Mathematica, you can certainly plug in the data like this as a list of lists, a list of points, 1, 2, 2, 4, 3, 5, 4, 7, like that. That's the quickest thing to do. You could also do X data, 1, 2, 3, 4, Y data, 2, 4, 5, 7, and then you could combine those and transpose the resulting matrix like this. Will give you the same thing that I typed into data. And then you can just do fit data, comma. We want a linear fit, so we use coefficients, so to speak. Well, a constant term, you might call it, and an x term, and emphasize the variables x. And there we have it, 0.5 plus 1.6x. Is the quickest way to get the answer. And what about R? So I hope you downloaded R. It would be good, if you haven't done so, to start watching the video that I suggested. I will be referring to things in the video. I forgot the guy's name who's in the video. It's his data sets, I think. But today we're just going to use RStudio. RStudio is an interface that makes working with R simpler, so you should also make sure you download RStudio. I know this is small. I haven't looked to see if I can increase the size of this yet. View, size, zoom in. Okay, we can zoom in with equal signs. Okay, that's a different thing. Let me make a new file, a new R script file here. So we have what's called an R script file, which is just a text file where you do your basic coding. The output tends to come down here in the console, though some output like plots come over here, and the variables are kept track of over here. If I want to put the X data in there, I could do something like this. You evidently have to use a C for concatenate, which essentially I think merges the numbers. So you can do C 1, 2, 3, 4. To enter that on a Mac, at least, you have to do a control return. I'm not sure how it works on a PC. So I'm about to do control return. And we should see output down there. Yep. Okay, so that's been stored. And if you want to confirm X is a numerical quantity or vector, you might call it, with entries 1, 2, 3, and 4. And then I can do something similar for Y. C stands for concatenate, which is just, again, combining the numbers. 2, 4, 5, 7. Control return to enter that. And with Mathematica, it's shift return, and with R, it's control return. And then if you want to do linear regression right away, it's LM, which stands for linear model, parentheses, Y, and then tilde X. And then do control return. And there you see in the console down here, the intercept is 0.5 and the slope is 1.6. Okay, so that would be the quickest way to do what we were doing, to find the slope and the intercept. And again, entering these things in the up here in the script file is control return on a Mac, maybe control return on a PC too. It's not command return. You'll have to either experiment or look it up to see what to do. But again, your output's down here for the numbers. Graphs can be made over here. You see the variables up here in the global environment. You can do other things too. If I do, for example, summary X, that gives me, for example, the 5-number summary for the X data values, as well as the mean, 2.5 down here. as an example of something else you can do. You can also make a histogram, although with so few data points, it doesn't really make sense to do so. And there you see a histogram of the X values. Hist does histogram. So those are a few basic things that you can do. Okay. As a little introduction to R, part of your assignment for Thursday will be to watch that video more, whether you've started or not. And we'll go into more depth. All right, we'll see you on Thursday.